how to do on Arch Linux. Anyway, today we're going to talk about shaders, how to make them from the bottom up, and and how to make a raymarcher, which is a bit of a different topic, but we'll get to that. First, I will show you the basic, very simple shader that I prepared. It's made out of three. Let's see, where does it go? Everything's a mess. I have an index HTML, which is just your regular indexed HTML that loads a script, and that's it. And then there's I have three. One of these index HTMLs is the ones that I should have. There, the shader workshop one. Yeah. So this is the index.js. And it. I'll just show you what it does right now. Can you all see this?
Yes.
Excellent. So this is not a raymarcher, but it's just a very basic shader thingy setup that I made. So I'll quickly walk through this program to know how you, run shaders in a website. Let's see. So first we got a Vertex shader, which is very simple thing. It just it gets what we're doing here is we're drawing a square on the screen, and all the colors and stuff that happen, they happen in the Fragment shader, which is the other shader, the Vertex shader is just the one that it gets called for each of the corners of the square, and it's responsible for the coordinates of those corners, and it simply gets those coordinates inside the attribute A, and then it multiplies them by 2 and subtracts 1. I'll explain why that is later. And then it outputs them in another vector U, which it does that calculation. And finally, it also sets the position, the actual position where on the screen it is, in the GL position variable. And that's the reason why. I'll get to that later. Why the -- 1. So here's the Fragment shader. It's again a very simple thing. As you might have seen, both shaders, they start with these two lines. This is boilerplate. The one says we're using version 3, and the other says something about floats, and you get errors if you don't do it. This is the boilerplate for using WebGL 2. So that's what I'm using, because in WebGL 1 you only get to use the very old GLSL 1 shader language, and it lacks a whole lot of features, and it's especially for raymarchers, you can do it, but it's no fun. This shader, it gets as input the vector U, which, as you may recall, is the output of the Vertex shader. So the coordinates, they get passed from the main program into the Vertex shader, into the Fragment shader, where the Fragment shader, it gets called for every pixel on the screen. So all the coordinates, they get interpolated between those corner points. I hope that makes sense. And otherwise, it doesn't really matter. Let's see, the output. I called it CC here because I like short variable names, but it stands for color. And apparently any output variable that is a vec4 in the fragment shader gets interpreted as the color of the pixel. So that's all we have to do in the last line of the main program of the fragment shader, is assign some value to the color variable, and then it, yeah, I will show you this very quickly by getting, I will first make the code a little bit bigger. Yeah, and maybe the letters a bit smaller. So, yeah, I don't know if you do know this or not, but see, if I put here a vec3 of 1, 0, 0, then the entire screen will turn red. And I have set my browser to auto refresh on save, in case anyone was wondering. And the thing here, this is just a formula actually for converting the color, which I can also set it to red here. But it converts the color to from linear RGB to sRGB by raising it to the power 1 over 2.2. This is just a thing. If you do it right at the start of your program as a post-processing step, then you won't have any problems. It just makes it a little bit different. Like if I make this color red half as bright, you get a color that is actually visually half as bright. And this is not the case for sRGB, that you get a different color red, I think slightly darker. But yeah, so by doing it straight from the start, we don't get any surprises with our colors if later on we decide to use linear. Sorry. So this is our fragment shader, and show one more thing that it can do. If we take like the x coordinates, put it in here, then you can see that the green value goes from -1 to +1, and you can see here I've clamped all the colors to 0 and 1, so the negative ones, it doesn't clamps them to 0. That's important if you're going to raise something to a power, because you can't raise negative things to fractional powers, at least not without using complex numbers. And so yeah, this is the very simple fragment shader. I will continue to show you how to initialize WebGL. So first I have here, and then I will return to the fragment shader and show how to make a raymarcher. Yeah, so the first thing is we got to create a canvas element. That's what this line does. It's a little bit convoluted, but that's because I made it really short. And the point is not that it's short. This was just a line that I had. You can make a canvas element anyway you're familiar with. We append canvas called C to the body so that we can see it. Then we ask the canvas for a context of the type WebGL2, and that's our GL object, and that's what we're going to use for everything now. First, I have here a function that compiles and creates a shader. Everything in GL is really verbose and annoying to do, so it helps to compartmentalize things a little bit. So yeah, this is my shader function. In most of my programs, it actually does a couple of different things it takes, for instance, it takes the source code as a string and it applies some transformations to it. So yeah, it doesn't really matter. So next is we're going to create a program. We compile the Vertex shader, the Fragment shader, we attach them to the program, we link the program, and we use the program. Thanks, WebGL. And then if something goes wrong, we give an error. We have to get the positions of our uniforms. A uniform is like a global variable that you set once for per frame usually. And it's all the shaders, they have access to these uniform variables. You can see them, I defined them here. Yeah, there they are. Uniform resolution, uniform time. The time is optional, just for if you want to create moving things. And the resolution is, yeah, kind of necessary. We'll get to that in a moment. So, yeah, where were we? We got the uniforms, and then this is really the most nonsensical part of WebGL. I don't know what happens here. But we create a buffer. We also bind the buffer right away, and then we buffer data something into the array buffer. And the point is that these are our coordinates. The 0, 1, 0, 0, 1, 1, 1, 0. Those are like the 4 coordinates of a square. Except that GL likes its coordinates go from -1 to +1. So that is why this line is here at times 2 minus 1. So this A variable is the input, and it gets all these coordinates that are 0s and 1s, and then it stretches them so they go from -1 to 1. This is something left over from Sculpture. It's shorter to do it this way. I could also put the -1 and 1 inside this list, and then I wouldn't have to transform them. I need the location of the coordinate attribute A. Enable the vertex attribute array. This is very important because otherwise your vertex attribute array isn't enabled. I bet you would have forgotten that otherwise. The vertex attribute pointer, whatever. So, and then it knows the coordinates. Now we have, the resize render function. It sets the size of the screen and tells it to GL, and then tells the program to start rendering. Here's my rendering function. It checks if we are running, and the time, puts it in the uniforms, also the resolution. And this is the actual draw command. This is what finally draws the things that we have all configured up till now on the screen. And it tells it to draw a triangle strip of 4 elements, and it doesn't really matter. We need the whole screen, and that's what we do here. And because this is an animation thing with a time, then we call the render loop again and again. There's a event for if we resize the window, so that it resizes the window, and it's good. And there's one that I can press space to make it stop rendering and start rendering again. And then we start the program. So this is a super short how to make a thing in WebGL that I did in 20 minutes. But I'm sort of assuming that most of you already know this or have done this. Time to make raymarcher. The first thing that I'm going to do is I'm going to make a new function that calculates a pixel. It's just how the program works. It gets as input UV coordinate, which is like the pixel coordinate, and I call it UV because I guess it's really confusing to do that, but anyway, this is what's called. And we also get the time, we call it T there. And this is where we calculate the color of this particular pixel, which is black right now. Then we're going to we're going to have to what is it? We'll get to that later. We'll find out, but there will be something wrong with the aspect ratio, and then we'll fix it. We'll do that in this line. We have the UV, so all we need here is to get a pixel of the UV and the time. If we save this, we should get a black screen. Very nice. Okay, now it's really time to make a raymarcher. This will take a while, probably. Is Will Stoll there, by the way? Because he writes one every day for practice, he told me. So that's pretty cool. First, we're going to define some stuff about the 3D scene, because that's what raymarchers are for. The first thing is a camera position, and we'll use a 3D vector for this. Let's see, how do I usually... I have the... the X and the Y are like your screen, and the Z axis goes in and out of your screen. I think, that's what I do. So the camera position, I'm going to be rendering, for starting, we'll start with a sphere and a plane underneath. So I'm just trying to visualize this. The X coordinate would be at 0 because we would be looking at it straight on. The Y coordinate would be at 5 or so because we'll want to be a bit above the ground. The ground would be at 0. And the Z coordinate is going to be, the sphere is going to be in the middle, so we're going to have to stand back a little, so I'm going to say -10. That's the camera position. Then we have another vector, which is, I need to tell the program that it's vec3, or I'll get an error. The look at vector, that's the camera and where we're looking at. So we know that the X coordinate is 0, the Y coordinate, well, if our ball is like, I don't know, I'm also going to say 5, and the Z coordinate is 0, that's where the ball is going to be. The 5 is just, we're looking above ground a little. Maybe not 5, so we're looking at 3, so we're looking downwards. That would be nice, this is our basic camera. We also need a thing called the zoom factor, which is about 2. We'll see where it goes later, but it's kind of like the focal distance, or what do you call it, where you have that with the vertigo effect. If they change something about the camera, well, I can show it later.
Field of view, right?
Field of view, that's a thing, yeah.
Or parallax.
Sorry, is it someone talking or just stuff in the background? Oh, okay. Let's see. So this is our camera. The next thing is, what we want to do is ray tracing, and it works. I should probably have prepared pictures for this, but I'm going to explain. Imagine you have your camera, and in front of the camera is a screen that's like your actual screen. And behind this screen is the 3D stuff that you want to render. And what we're going to do is we're going to shoot a ray from the camera through each of the pixels of that screen. Then we're going to see what it hits in the 3D scene and color it accordingly. Yeah, that's the basic principle of a ray tracer. And ray marching is a specific technique to make the tracing of these rays easier, and we will get to that later. So what we now want to do is we want to sort of create an axis system around the camera. So we know, yeah, we need axis. We need a vec3 that is a forward pointing vector. And let me quickly explain about vectors, because see, vectors in GLSL are just 3 numbers, or 2 numbers, or 3 numbers, or 4 numbers. See, in the case of the variable col here, the 3 numbers mean an RGB value. But in the case of camera pos here, it means a coordinate in space. So you can see that there's various interpretations of what a vector means. And there's this one specific interpretation that's sort of like a coordinate, but it's more like an arrow. So you have to visualize like you're sitting at the origin in 3D space. Your vector is somewhere at that coordinate, and it means that's an arrow from the origin towards that point. I hope that makes sense. If not, I'm sorry. I'll explain it again. Point is that we have the forward pointing vector is simply the look-at vector minus the camera position. Now we have an arrow going, that represents like the distance between the camera position and whatever we're looking at. However, in the case of what we're going to do next, we would like our axis vectors to be length 1. So that's what we call normalizing a vector. What normalize does is it simply takes the vector, calculates the length using the Pythagoras, and then it divides the vector by its length so that the length becomes 1. So this is the forward pointing vector. You have to imagine this as a tiny little red arrow pointing out of the camera. There's another vector that's the right vector. This vector is like our x-axis of the camera, and it points to the right. And how are we going to figure this out? Well, we got this very useful function called the cross product, and the cross product, I'm not gonna tell you how to calculate it. It's not difficult. It's really fast also. But what it does is it takes 2 vectors, so 2 arrows, 2 pointy little arrows, and it tries to come up with a third arrow that points orthogonal to the other 2 vectors. And it finds the one according to the right-hand rule, but that doesn't really matter. In this case, if we take an arbitrary vector that points up, just towards the sky, and we cross it with the forward vector, then we get a vector that points to the right. And I'm not entirely sure if the result of the cross product in this case is normalized, so I'm going to normalize it just to be sure. Oops. Finally, we need the up vector, which is simply the cross product of the forward and the right vector. It's just once you have two normalized axes of a coordinate system and they're orthogonal, then you can just cross product them to find a third. And you don't even need to normalize it. This is linear algebra stuff. So now we have a camera, we have a whole bunch of arrows that point around it. What we now want to know is if we shoot a line from the camera through the current pixel, what direction would it have? So we call that direction, we call it RD for ray direction, and it's again a normalized thing because we're going to create it out of the three axes that we just made. So we're going to take the pixel coordinate x and multiply it by the right vector. We're going to take the pixel coordinate y and multiply it by the up vector. And finally, we're going to take our zoom value and multiply it by the forward vector. And that's why the zoom factor, yeah, it sort of makes the ray go faster, kind of, but it's forward pointing, except it gets normalized, so it doesn't actually become bigger, but you will see what difference it makes if I adjust the zoom later. And it does adjust the field of view. So now we have all that we want to know for our raymarcher, or for the ray tracer to do its thing, and we can shoot a ray in that direction, and we want to know what is. See, we know the distance we know the direction of this ray. So all that we need to know is the distance, how far along this ray before we hit something. That's what we want to know. So we want to, d for the distance. And we're going to write a function called intersect, which is, that one's going to do ray marching. And I actually have some pictures prepared for that part, because this is a lot of code and there's nothing to see right now. And I'm sorry for that, but I don't know how to make it more step by step. So we have the intersect function. It gets a couple of parameters, like from where do we shoot the ray, in which direction do we shoot the ray, and let's see, do we need another thing? Yeah, it needs to know the time, because this scene that it's intersecting with, that's the thing that is moving, so it needs to know what time it is in the scene to know if there's an object there at that particular moment. I think that's it for the. Now we can find the point of intersection, which we will call P, which is simply the camera pose times plus the ray direction times D, and then we arrived at the point in the scene. Yeah, I'm just going to show you some pictures now, because otherwise I think this is getting way too abstract. Is everybody still following what I'm trying to do here?
Yes.
Yes.
Cool.
One question though.
Yeah.
I think I know the answer, but line 28, you have W instead of vec3. I think that's one of your defines, right?
Where is
so
it?
The cross, then it's W010.
Yeah, I shouldn't have that. I shouldn't. I normally have a whole bunch of defines for to make typing quicker and the code shorter, but I was not going to do that this time.
Yeah, I assumed that.
Thanks. But it would have given an error. Yeah, so I'm going to show some pictures about raymarching now, which is, they're from a presentation by Inigo Quiles. He, well, I probably mentioned him a lot of times. He's the raymarching god, or at least extremely good at it, and personal hero of mine. So in this case, the camera is at the position of the blue circle, the blue dot, and it wants to trace a ray in the direction of the black line. And well, we know the direction of the black line, we just don't know how far along the black line we need to go. So what if we had a function that tells us for every point in space how far away the nearest object is? That would be pretty useful, because if we knew that distance, we would know the distance is this much towards the first wall here, and that means that we can step at least this far along the line, and then we'll sure not hit anything. And then when we are at that point, we can ask again, what is the closest distance to any nearby object at this point? And if we get that answer, we know, like, oh well, it's this wall, but we don't know that, or it's this wall, we don't know that, but what we do know is that we can at least move this far. Can you see my cursor, by the way?
Yes.
Good. I'm never sure in Linux. So and again, at that point we ask how far away is the nearest object. We can move this far again, until we hit something, and we know we hit something when the distance we ask for is 0, or at least very close to 0. And this is the fundamental concept of raymarching. And the function that you ask how far away is the nearest object, that's called a distance function. And in particular, it's usually called a signed distance function, which means it's negative when you're on the inside of an object, which is sometimes kind of useful. And the abbreviation for that is SDF, and you might have heard that term a couple of times in the shader channel. And I'm going to show you some SDFs once I get this raymarcher done. So this is the basic concept. This is what we'll be doing in our intersect function. And we got the position. We want to know a couple of other things before we can calculate the color, but we'll get to that. I'm going to write this intersect function now. It returns a float, and it gets as the input vec3p, where it starts, and the ray direction and time. I'm gonna call this time here. No, t like that. Yeah, I want to call the other thing t. Let's see how my intersect function. How do I write it again? Yeah, it's. This is the thing. If you're in WebGL 1, this is where it looks slightly different, or does it? Well, I'm not sure. We're going to do this with a for loop. We'll have a variable called t, and it starts at 0. T is like the distance, how far along the line we're traveling currently, starting from P. And so how far are we going to trace is something called a max dist, which is, we can define it here. And let's say it's just how far away the furthest thing is. Let's say 100. Our scene is not going to be that big. Yeah, and then for the last bit, we're going to leave this empty because we're going to increase T inside the loop. Now, first thing is, what we're going to ask is, how far is the closest point? And that variable we're going to call h. I don't know why, but they usually call it h. And we're going to call a distance function, which I always call df because it's short. And df needs to know where we are currently, and that is p. Oh wait, I just remember, usually they call this one RO. I will just use the same variables everyone uses. This stands for ray origin, and so it's the ray origin plus the time times RD, how far we are along the line, right? And this distance function, because it defines the scene, also needs to know the time, needs to know what time it is, so that if we are going to move things, we can move them. Then, if we know this distance, then we can add it to t, and thereby move that far along the line. The final thing, what we're going to check is if we hit an object, then we should stop. So that happens if h is smaller than another constant we call surf dist for surface distance. And this is like a small number that, maybe not that small even, which is like if we're this close to a surface, we hit it. If that happens, then we hit the object and we want to know how far along the line we were, so we return t. And that's it for this loop. Finally, if we make it to the end of the loop and we're still didn't hit anything, we're going to return the max dist. Yeah, that's our intersect function. It's really that simple. Let's see, what am I going to do now? Need the distance function. I also need some way to color the scene. Yeah, I'm first going to color the scene, which, let's see, how do I do that? What we need to know is the another vector called the normal vector, and it's like if you hit a surface like a sphere, you have to imagine like this very tiny pointy vector pointing perpendicular to the sphere. That's the normal vector. It's all these, it tells you how, the orientation of the surface. That's the information that you get from the normal. And we're going to make a function to do that. What it needs is at which point we want the normal, and of course what time it is, because everything might be moving. So yeah, we have here a vec3 normal, so it has these parameters, the p and float t. And now is the question. yeah, the normal, I'm just going to copy this. I can explain this, but I'm going to copy it because it's a bit of magic. But what it does is it evaluates the distance function in, where did I go? Here. It evaluates the distance function in the area of the point that you're asking about, and by subtracting those values from each other in a clever way, you get the normal. And this is a way to do it with only 4 points. It's a method that Inigo Quiles describes on his website. And I can explain more about that later, but it's not really important right now. Yeah, so this is the normal. What we now need is the lighting, right? Yeah, so we need a light position, which is light pos. So we're going to imagine this is somewhere above our sphere to the left with -15, and it's quite high in the sky, so maybe 30. And it's a little bit between us and the object, so at -5. There, that's where the light position is going to be. Because what we can do now is, yeah, we'll calculate the diffuse lighting by taking the dot product of the normal and light direction. And I will explain that in a moment. We will now calculate the light direction, which is simply, let's see, it goes from the light source to the point, or the other way. Well, I'll get it wrong and then I'll put a minus sign somewhere. This is the direction that the light goes in, and we want to normalize that because normalized vectors, the normal is a normalized vector, the light direction is a normalized vector, and yeah, I'm gonna explain something about the dot product. It's the best product. First off, the dot product is very simple to calculate. You can, if you have dot of A and B, you get A dot x times B dot x plus A dot y times B dot y plus A dot z times B dot z. That's it. This is the dot product. And it also happens to be equal to the cosine of the angle between A and B times the length of A and the length of B. That's linear algebra. This is just the case. Because our vectors are normalized, the lengths are 0, so we can take this off. And what we are left with is the cosine of the angle between the normal and the light direction. And that's a really nice thing to have, because if the light hits the surface straight on, then it's in the same direction as the light direction. And the angle is 0. And as you know, the cosine of 0 is 1. Also, when the light hits the surface at like, yeah, it doesn't really hit the surface at this very low grazing angle, then the angle is like about 90 degrees, and the cosine of 90 degrees is 0. So you can, this is also the way that light works. The only thing is that cosine can go below 0 and light doesn't do that. So we will take the maximum of 0 and this, right? Yeah, I always get confused if I have to take the maximum or the minimum. But then we have then we have sort of like a light, and that's a gray light, so we can return this. We can make a vec3 out of it, and it will just copy the value 3 times, which means we'll get a gray value that is equal to our light, which means that once we get everything done, we should see something. If I'm correct, the only thing we still have to write is the distance function, and that's easy. We can write a distance function. It needs p to know where it is, and the time. We're not going to do the time right now. First, we're going to make a sphere. I'm going to call it S, or sphere. Okay. What's the distance function for a sphere? And I should have made some pictures for this, but it's equal to the what's it again? The length of the distance from the center. So that, let's see, we'll define that later. The length of the distance from the center minus the radius of the sphere. If you think about it, that makes sense, because then if you're exactly at the radius of the sphere, then the distance function is 0. And if you're outside the sphere, it increases and increases. And if you're inside the sphere, the distance is smaller than the radius, so it becomes negative. So this is a signed distance function, and that's what we want. We just need to put the center somewhere. It's a constant. And where were we going to put that again? At x0. We were looking at 3 above the ground, so that's also where we're going to put this the thing, and the z is 0, and then where the radius is a float. We're going to make it rest on the floor. We haven't made a floor yet, by the way, but so its radius will be 3. If everything works, we should be able to run this and see at least some kind of sphere-y circle thing. We did get an error. Good. Int const height float. That means I forgot a dot somewhere in line 9, which I can't tell somewhere. Let's see. Do I need to put dots at all these? I thought I didn't. Oh, I need to put it here. Yeah. Let's see if it works now. Does not return a value. Oh, that's correct. Now comes the debugging part. I'll fix this. RD syntax error. Oh, right.
Also, line 42, there's a double definition of the function name.
Oh, yeah.
And the t is defined as tt in the rest of that function.
That's also bad. Thanks. Let's see, where do you go? H syntax error. Times H. Oh, and I need to my defines here. This is float, and this is a vec2, and this one says normalize. There we go. Again, v. There one. So normal variable expected. Dot. Okay. Vec3 is normal pt. That looks like it's correct. Okay, and the dot is no. Where's the dot here? Norm, comma, light there. Oh wait, that's yeah. This is called n. Hey!
Oh, cool.
Okay, so this works.
Cool. Awesome.
Yeah. Next part is I'm gonna add one thing to the distance function, which is a plane. Distance function to the plane is also quite easy. It's simply p.y because we're going to have a plane at 0, and if we're above the plane, then y goes up. If we're below the plane, y goes down. Now we just need to combine the sphere and the plane. In order to combine two distance functions, we always want to know where's the closest point. So we take the minimum of these two functions in order to combine them. And if everything went right, we should see a plane. Well, there's something. And yeah, this is the raymarcher. I did it in an hour. That's pretty good. I think it's good that I will show some cooler tricks that you can do with raymarchers in a few moments, but I think it's good to see if there's any questions or people followed this up to now.
No, this is very cool. Thanks for sharing. Unfortunately, I have to hop off. I'm technically working. I have a meeting coming up, but very cool. And again, yeah, thanks so much for the tutorial.
Yeah, no worries. I'm recording everything, so you can check it out later.
Oh, that's perfect. That's perfect. Thank you.
Hi, Peter. The result is awesome. Thank you so much for the workshop. I wonder if you can share the code after that, because I was on the go and I wasn't following all the time.
Yeah, definitely. I will share. I will put it on GitHub probably or something.
Yeah, getting the canvas, all of the OpenGL, the WebGL stuff set up would be really helpful for me. I've never done this in a browser. I do a lot of GL on the OpenCL in the back end, but this is very cool.
If I will put this whole folder in a GitHub repo, and there's also a backup file of the original index.js that I started with, so you could even see the minimal setup code. So yeah.
In your when you calculate the normals.
Yeah.
Why do you take that fourth point in your normalized function? I've only ever taken 3 points, like dot xyy, dot yxy, and dot yyx. Why do you take that fourth point at dot xxx? Sorry, I joined late. If you already explained that.
No, I didn't explain it. I just I mentioned it's a technique by Inigo Quiles, and I will show the article because he explains it way better than I. Thing is that so this is the classical normal function, I think.
Yeah, that's what I'm used to seeing.
Yeah, and this one has in total 6 evaluations of the distance function, which is usually the most expensive thing in the program. And so they came up with another technique, which is the tetrahedron technique, which samples the points from the vertices of a tetrahedron, which is the 3D simplex. And if you you can also calculate the gradient of the distance function this way, and you only need to evaluate it 4 times, so it's a bit faster. And it, so far as I've seen, it works just as well, which is kind of weird because you'd think you get.
Oh wow! I came up with this approach by myself. It's fun.
Then you should be very proud of yourself. That's amazing.
Thanks for explaining that, Peter.
Yeah, no worries. So yeah, that's the normal. Let's see, what can we do now? Well, usually I go to the page of Inigo Quiles' website because he has this amazing page called the 3D distance functions, and it just has the distance functions for all the shapes that you want, all the simple shapes, and even a couple of complicated ones. And yeah, so we've seen here the sphere, and now I want to make a box, so I will copy this function. I will change it a little bit. Let's see, we'll just put it above here, because I don't like the way Inigo formats his code. And this function is just called box. And otherwise, yeah, it's fine. Yeah, to explain this function would be a little bit difficult, but I do believe that, Inigo has a YouTube video about how to derive the distance function for a box. It's very useful because boxes are cool. And I'm going to now, I'm going to replace the plane with a box because I want to have a square underneath it. So we're going to be, the box is also centered at 0, so you always subtract where you want the center of the box to be. In this case, I want it to be 5 big, and I want it to be with the top at 0, so it needs to be 5 below the ground, so at 0 minus 5, 0. And the other parameter is how big the box is in 3 dimensions, so you can also make rectangles, but in this case I make a cube of 5. And if I did this correctly, now we should see a box instead. Yeah, so now you can see that the plane is not infinite. We can also move the camera. We can actually, yeah, we could even move the camera like around it and make it moving, but nah. We'll go a little bit to the left to see everything, and a little bit up, and a little bit further back, and shit, where are we now? I think I'll go farther to the left because I want to see the light side of the cube. Yeah, that's nice. Yeah, there's another shape that I like a lot. That's the donut. It's a very simple shape. It's like for SDFs, it's the second simplest formula, I'd say. I mean, the box is pretty complicated, but the sphere is really simple, and the donut is also really simple. So we have the coordinate. We need to know the inner radius and the outer radius of the donut, and this is equal to the length of how does it work again? Yeah, of the length of p dot. How do I want my donut to be? I want it to be in the ZX plane. Yeah. Minus the 1 radius, comma p dot y, the 1 coordinate left, minus the outer radius. This is I could explain how that works, but it's like the middle part is, so if you have a length of p.xz minus r0, this is the two-dimensional distance function of a disk. Right? It's the same one as a sphere, but then for a disk. And what we then have is, well, this disk, but I forget how this works again. I might even have gotten it wrong, but yeah, well, if you add the y-coordinate to the disk, then it sort of bubbles up again. What does it do? It yeah. Well, I'm sorry. I in my head this makes sense. Well, anyway, we got the donut, and I'm going to put the donut here with the p. Oh wait, that's yeah. P minus center, and then a radius. Yeah. Tell me. Oh.
Yeah.
I
You
did
have
make a mistake.
R1, which.
I did make a mistake. This is not what the
should
donut
follow,
should look like.
No, it's inside. Yeah.
I'm going to.
R1 should follow like.
Yeah, probably. Oh, that's it. Yeah. What am I subtracting it of now? Of the vec2? Oh, that doesn't make sense. Yeah. Yeah. So this is actually funny because what you can see now, this is like a circle. We got a circle without anything in it. And if we were to inflate this, we would get our torus. And you can inflate any object that has a distance function simply by subtracting a number from it. If you think about it, it makes sense, right? If you subtract from the distance function, everything gets closer, so it inflates. And that's kind of what we're doing here now, and now we should have a donut, yay. I can, for instance, demonstrate the inflation when I subtract a small number from the box. We should see that the box is now has round edges because we grew it slightly. Yeah. What else should I explain? Oh, there's a cool thing that you can do if you... yeah, we're going to make this weird donut now. Call it X donut to be sure. Like if we have the y-coordinate of our... see, what we're now going to do is we're going to transform the domain of the whole space. And if you do that, it still works. You get distances. And I can... see, I will show this in Desmos first. To the graphing calculator. See, if we have a normal, yeah, our normal coordinate, y, it's going, well, it's just going. It's on the x-axis here, I think. But anyway, the point is that for this donut, something happens around 0. That's where the donut is. And if we if we take the absolute of x, we get something like that, and we can move it around a little. For instance, -3, is that work? No, I have to here. Yeah, -3, and then -1 or 2 or 3. Yeah, like that. See, now we maybe I will make this 2 and 2. Yeah. So what we see now is we have a function that it goes, it does this, it goes to 0 here, but then it goes to 0 again here in the other way. And this is, if you do this to a distance function, that means you're actually like, imagine there's a mirror here in the space. That's basically what you're creating. So if we do that to our donut, the y coordinate of the donut, if we do it to that, we take the absolute value, we subtract 2 and we subtract 2, we get that that bend function. We should see 2 donuts now. Yeah. And the cool thing about distance functions is that you get this almost for free. It just costs 1 line of code to change the coordinate system, and it just copies everything. If the donut had been a more complicated shape, then it would have copied that too. In fact, we have a complicated shape. It's called the distance function that we have. It's made of a donut and a cube. If we do it at the start of our distance function, like this, we're also going to mirror the cube, and it should appear like here at the top of the donut. No. Well, something's mirrored, but it's mirrored the other way. Still cool. So you can do that. I'm not going to do that. I'm going to make it like that. And the donuts can be a bit thicker. Yeah. I was going to demonstrate the zoom value because I want to get closer anyway. So if I increase it, everything gets closer, but you don't actually get closer. It's more like it zooms in on the screen, which is very useful if you want to put things into focus. I want to show some cool shapes now. We have a sphere and a donut, a double donut. Wait, we'll call this one now the X-don, and plane is BB for the box, or otherwise that's really confusing. So we have that one, and now we're going to make a sphere like this. That's length of p minus center. We're going to put it at the same place, and we're also going to make it about radius 3. And we're not yet going to put it in the distance function. What I want to show is another trick by, is it by Inigo Quiles? It's just a trick that you can do with distance functions. And it also involves the absolute function. But it's what happens if you put the absolute function around the entire distance function. And so that all the distances are positive. What does that mean? That means that you now have like if it was a sphere, you now have an infinitely thin shell of a sphere, because it's the distance goes to 0, but then it goes up again when you're on the inside. So this is the sort of object that you have if you took the absolute of a sphere. But then if you were to inflate this object, like subtract a small number from it, you would inflate this shell of a sphere, and you would end up with a thick shell of a sphere. And so the taking the absolute of a distance function and subtracting a small value from it, it Yeah, you can't see the sphere anyway. It makes, now we have a hollow sphere. You couldn't see the difference, but we're also going to do this to our X donut. We're going to make it hollow. I'm going to use 0.2, so they'll be relatively thin. Because there's a fun thing that we can do. There's another, look, we have the minimum operator, which takes like the union of several objects in a 3D scene. But we can also use the maximum operator, which calculates the intersection of two objects, which is a really cool operation. Wait, I will do this first. I will not make these shells. I will just show you what the intersection of these two donuts and a sphere looks like, because it's somewhat easier to imagine. So we have the X donut and sphere. And then we take the minimum with the box on which everything sits. So now we have, this looks bad. Whoa, what's going on? Maybe it's that it's just barely touching on something. I will, oh, maybe I should make it bigger. That's kind of weird. I will, well, I will look at my sphere. That's a sphere. I'll make it a bit smaller. Yeah. And now I have the X dome. Oh, that's quite big. Oh yeah, we need to put our sphere, we need to put it in between the donuts. So these donuts are now, I think that's at 4, or I don't know. It's higher up than 3, that's the point. I will make it 5. And then we can make a sphere of size 5. And that's about the same size. Yeah, if we now take the intersection, it should look like something. Yeah, this looks like the intersection. You can see that it's both the donuts and the sphere, kind of. Now comes the cool stuff. If we're going to make this thing hollow, and we're also going to make this thing, who can even imagine what it looks like? I sure couldn't, but this doesn't look that good yet. Still, it's kind of interesting. Why is this not yet? Maybe the sphere should be slightly smaller. Nah, it's just boring. I should yeah, it just means that I gotta put something more interesting than a sphere there. Oh, let's look at the sphere again. I'm going to try with this another donut, but this time I will put them, I will swap the X and the Y coordinates, so they're standing up. I just have to minus center, and I think I have to swap this one in the same way, or else it doesn't work. That's like this. Let's see. Hey, that actually worked. Well, not really. Maybe I shouldn't shuffle these in the same way. No. They're a bit off to the side. Well, that's... yeah, that kind of makes sense. Well, then they'll just look hideous. But it still will look like something if I make this at the shell, they, huh? Why'd they just move? IX set and then. Oh wait, I was IX set that one, yeah. So now they're going there, -0.2. So if I see, they get slightly thicker because of this shell effect. I hope that now it will look like a weird shape. Yeah, that's getting somewhere. So this concept of making intersections of hollow objects was the basis for my sculpture project and on art blocks. And yeah, that's what I wanted to share about SDFs. I think it's time for questions. Anyone?
I don't have any questions per se, just commenting on the story. I could actually follow it.
Thank you.
I now understand what SDFs are about. Had a sort of a gist about what they would be, but yeah, I understand the fascination of so many people about these things. It's cool stuff. It's going to be my next topic I'm going to dive into, I think.
They're also even, I use them in 2D as well, often for, it's very useful to have an SDF for instance, the frame of your picture. Like if you have a margin, you can calculate if points are inside or outside, or you can even scale things if they get too close to the border. And I use that for Hypergiraffe, where I combined SDF with some wobbly functions to make them, but it's like a wobbly function that's intersected with the margin of the page, and that it's just a very convenient way of thinking about things.
Yeah, I have to rearrange some cells in my head to get a complete grip of how to deal with this, but this has been a really good start. Thanks for that.
You're welcome.
Are you going to go over how you manage or do different materials? Like the way I do it, I mean, I assume other people do it this way too, but instead of floats, instead of my SPS being floats, they're vec2s, and then you just give it like a different number as the Y parameter, so you know which object it is, and you can keep track of materials that way. Is that the same way you do it?
No, it's a way that I've seen people do it, but well, I didn't like it. It just, not for any particular reason, but it's just its programmer style itch. The thing that I usually do is, let's say we want to make the cube red. What I usually do is, so I have the cube, I put it in a function like this, and I put it here, cube vec3p, and then I will in my here where I calculate the pixel, I will calculate like a float. Now, if it's the cube, we use a step. I use a step function of. Let's see. We're gonna 0. The step function, it first takes the threshold and then the value. So the value is the distance function of where we are of the cube. So now knows it's either 1 or 0, whether it's in the cube or not. And then we can have a vec3 call for color is the mix between, well, we want one color is, say, red, about this red, and vec3, and the other one is 0.4, 0.2, 0.9. That's blue, and then we mix it depending on the value of cub. So now we do the diffuse times col, and they should have different color. No. Oh, wait, I don't need to step with 0, but with the surf distance, because it's that far away. Yes. See, now I did 2 materials. And I'm not sure if this is a better way of doing it. It's just the way that I happen to do it.
Yeah, it's definitely very different than how I do it, so it's really interesting to see. Did you say you were going to share this code? You're going to put it on GitHub?
Yeah.
Okay, cool. Thanks, Peter.
So, yeah. Any other questions or things you want me to show that aren't super difficult?
Yeah, this is just out of curiosity. So, if you have the situation with the two donuts,
Yeah.
and you inflate them.
Mm-hmm.
So you inflate them both. Will the part where they start to intersect, will that be a sharp corner, or will that also round off?
Good question. Most of the things where you hope it'll round off will probably be sharp corners. This is because the distance function actually starts becoming incorrect as you're doing stuff to it. It's, yeah, again, best explained by some images by Inigo Quiles. Let's see, the interior SDFs explains it very well. Yeah, you can see here the difference is there's like a slight difference between correct and incorrect. Yeah, the point is that if you imagine what the distance function of a cube looks like, for instance, is that on the outside of the cube, it is round. The distance function is round. You know, it's like the distance from the point of the cube that you're looking at. While on the inside of the distance function, it is more angled because you're always trying to see which face of the cube you're closest to. And this has the effect that I can show this actually. If I, let's see, I will just, yeah, I will copy this and I'll show just, this is just a cube, and where's the cube? Cube here. If we don't inflate it, it is sharp. And however, now comes a funny thing. We can also reverse inflate it, so deflate it. So we can add a little bit to it. And you will see that it, even further, it just becomes a smaller cube, which makes sense, right? Mm-hmm. However, let's say we're trying to inflate this smaller cube, and we subtract 0.3 from it. It's not round. You see what happened? So there's differences and inaccuracies like these are slowly building up as you manipulate distance function formulas. And the real trick of doing it is like keeping those weird edge cases to a minimum. And these are just these are okay with errors, these because they still give bounds to the distance, so you can ray trace them properly. And it's also important to know what are the constraints on your distance function. What does it need to do? For instance, if you want to shoot an intersect, if you want to use an intersect function, you need quite an accurate distance function. It shouldn't like mess around or get really weird in some places, or it won't step through properly. However, if you're using, say, a 2D distance function and you're just checking for every pixel if a point is inside or outside of a shape, you just need to know if it's positive or negative, and whatever the distance function outside, you don't care. It just needs to be the right sign. So there's different constraints for different purposes, and that gets really tricky sometimes.
Okay, thanks.
There. Everything is back. Well, if nobody else has questions, then I think I'm done.
Well, again, thank you very much. Really appreciate this.
Yeah, it was a lot of fun.
Woohoo! That was great.
Thank you very much. I will I will upload the video to YouTube and put it on GitHub, everything. And see you in the chat.